thank you for coming. Here I want to share some of my understandings about the earthquake sources, especially how complex they are. As Luke just mentioned, it's a wavy stuff, right? So when an earthquake happens, the background is an image of the surface fault ruptured by the Turkey earthquake occurred 2 years ago, and it generated a 300. Okay.
Yeah, we forgot.
Okay.
We know each other too well. So.
Sure. Okay, now you can hear?
Yes.
Yeah, that's great. So it generated a 300-kilometer long scar at the Earth's surface. To me, when earthquake happened, the Earth's crust is like a crime scene. The criminal left, but it left a series of evidences and clues such as the fault, the ground deformation, and the wiggles, right? Wiggles by wiggles. So that's the way, as an earthquake seismologist like me, try to look into these clues and try to get to know what the criminal look like and understand the next time where it will be. Well, it's a theoretical best expectation, but in practice it's always very difficult. Otherwise, I will not be here, right? So we all know that earthquakes are among the most deadly natural hazards, but to what extent? The left figure shows the annual average global deaths from a series of different natural hazards, including the droughts, floods, earthquakes, storms, and a lot of things. In the past 100 years, starting from 1920, we can see that thanks to the improved infrastructure and food security at the global scale, we have done a very good job in trying to mitigate the drought and floods as the biggest challenges. But since 1970s, the annual deaths of the natural hazards remains more or less flat. It poses challenges for us to mitigate. And the most important contributor are the red histograms, the earthquakes. And we all know that earthquakes are difficult to mitigate because we cannot we cannot prevent earthquakes, we cannot predict their occurrence. But another thing is that maybe earthquake occurrence or reoccurrence spend quite a long time, sometimes hundreds of years in a location. But if we take a look at the global scale, there are so many faults, so many regions. And actually, we are experiencing devastating earthquakes year by year, sometimes a series of them in 1 year. So the right panel shows the devastating earthquakes collected since 2000. X-axis is earthquake magnitude. The y-axis is the deaths per earthquake and its subsequent tsunami. Many of those caused hundreds to thousands of casualties. And in 2023 only, we had earthquake in Turkey, Syria, Morocco, and Afghanistan caused tens of thousands of deaths and huge economic losses. So this year's Myanmar earthquake occurred several days ago is another example. It's really, really devastating, and the final death toll may be comparable to the Turkey-Syria event. So our civilization have always been trying to fight against the earthquakes, and we have been trying to come up with some mitigation strategies. One of the most famous efforts is to try to predict earthquakes, right? I know as a seismologist, talking about earthquake prediction is somewhat sensitive, but I still want to show that there are examples of so-called succeed. In 1975, there was a magnitude 7.3 earthquake occurred in Haicheng, northeastern China. This event actually caused around 2,000 casualties, but I used only here because if there was no evacuation order by the government, it can easily kill hundreds of thousands of people. And what are the predictors? It's cute. The snakes, frogs, and boiling wells, right? It may sound incredible, but it is what it is, and there are data support. The earthquake occurred on February, and about 1 month ago, there are increasing number of records of abnormal activities of these animals and the groundwater levels. About 2 days ago, before the earthquake, the groundwater level abnormally have suddenly increased the number, and it directly drove the government to send the evacuation order. So this is some good sign, but is this sustainable? Unfortunately, no. because 1 year later in Tangshan is another city near the northeastern China, quite close to the previous earthquake. A magnitude 7.5 occurred, and this time there are no precursors, no animals talking, no groundwater boiling, and eventually it caused over 200,000 of casualties. It remains one of the biggest damage in the modern China. So now from our current point of view, we know, these predictors are somewhat arbitrary. They do not really have a lot of physics inside. Maybe a little bit, somehow associated with a pre-earthquake aseismic slip, but it's very hard to identify, even with the modern instruments. So then, is there any way for us to get the physics? For those of you who have attended John Phillips' talk several weeks ago, you may remember the cute video that her daughter is trying to pull the block, and the block sporadically move. Here I'm going to play the same stuff for those who haven't seen that. The idea is that the earthquake is like a stick slip behavior, because the tectonic loading is somewhat more or less constant, and it gradually builds the stress up to contest the frictional resistance. When the stress is large enough, then these rocks start to slide, and for the earthquake scenario, the earthquake happens, the stress starts to build up again. So in this case, this zigzag indicate the periodic nature of the earthquake occurrence under the condition of the nearly constant stress loading. So now we have a physical model. Actually, it worked quite well. It is one of the fundamental models of the earthquake physics. However, does it really provide us a good capability of prediction? Sorry, it's not a good ending here. Actually, scientists have attempted to do the prediction, and they choose a location called Parkview, which is near the center portion, but slightly to the north of the San Andreas Fault across California. The Parkview is a spatial location because at the southern part of this location, there was a locked segment due to the, identified by the 1857 magnitude 8 earthquake. To the north, it's a creeping section. Creeping means that the fault are sliding constantly, and they cannot accumulate any stress. So the boundary conditions are there, and then the tectonic loading is constant. Then why the earthquake should not be recurring, right? And since 1857, we indeed see a lot of events. They repeatedly occur at the same location every 20 years. So in 1966, the seismologists are very excited to build up a plan to deploy seismometers, to deploy geodetic observations, and they build strong connections with the local farmers and landlords. The connection is so tight long after the agreement expires. Why the agreement will expire? Because the earthquake did not come on time. Eventually, it takes additional 16 years until 2004. The earthquake came there, and it's not ruptured in the expected way. It ruptured the opposite orientation or directivity. So among the farmers, there was a joke that their harvest of the grapes and cherries are even more robust than what the earth looked like. Somewhat, I agree with this idea, and we can take a look at the cumulative strain at the San Andreas Fault coming from the paleoseismological record. The x-axis is the strain, y-axis is the time. It is a 2,000-year record. So we see that this zigzag are the earthquake occurrence and the interseismic period. They are very complex and irregular. So it means a big challenge in front of us regarding the earthquake predictability. So where the challenge come from? Why the earthquake problem are so hard? To me, it somewhat remains one of the highest pinnacles in the earth science, if it's not the whole science, because it really spans a broad spatial and temporal scale. Especially the earthquake involve the asperity contact area of micrometer scale. Then we can expand it a bit to the localized shear band and the fault roughness to the sub-millimeter scale, and then to the fault damage zone to the meter scale, eventually to the long fault, sometimes can extend hundreds to thousands of kilometers. Temporally, the earthquake nucleation happens in a very short time frame, sometimes in the milliseconds. Then the earthquake ruptures, it can extend seconds to hundreds of seconds. The wave effect and dynamic stress perturbations can extend for like minutes to hours. And eventually, the pulsatile deformation takes days to years. Finally, the earthquake cycle costs hundreds or even 1,000 years to see the earthquake's reoccurrence. Besides this very broad spatial-temporal scales, the earthquake also very rich in terms of its driving physical and chemical processes. We all know that the geodynamics is certainly going to play an important thing because the Earth are a bunch of plates. They are moving with respect to each other like jigsaws. They rub each other, they generate plate motion and cause the earthquakes. But also crust rheology play an important role because when the temperature goes higher, pressure goes higher, the rock strength first go up and then goes down. First allow, then prohibit the failure of the earthquake. And fracture mechanics is something that we need to consider because to sustain the rupture, we not only need the fault, but we need the strain energy to be available to be not only emitted as seismic wave, but constantly be injected into the fracture tip to tear off the rocks. We also need to consider some heterogeneities, such as the fluid-related processes. It can change the pull pressure, change the chemical conditions of the fault, and eventually generate some time-dependent issues. So all of the things may contribute to the earthquake source complexity, and how do we deal with it? The plan is here. We should first be able to see the complexity, then we should be able to quantify it. We further probe into the environment, and finally, we want to replicate their dynamics. So talking about the first step, see the complexity. Here I choose an example of the megathrust earthquake. The reason is that megathrust earthquake is can usually be large. They account for over 70% of the largest earthquakes among the world, and then can cause huge tsunami threats. So in 2021, a magnitude 8.2 earthquake occurred in the southernmost region of the Atlantic Ocean, where the Atlantic plate is subducting beneath the small South Sandwich plate. This plate is quite small, but the subduction zone is quite long. So at first, USGS reported a magnitude 7.5 earthquake. We don't think it's a big problem because it's a remote region, far away from coastal communities and cities. And a magnitude 5 earthquake generated tsunami at a comparable depth is usually regional. However, when they passed, the tide gauges at 3 major oceans recorded a noticeable tsunami height of over 20 centimeters, and it reached as far as 15,000 kilometers of distance. So it's essentially a global spreading tsunami. What's wrong here? Then the USGS reported another event with a magnitude 8.1. It was supposed to occur only 3 minutes after the first 7.5, but was reported 1 day later, and this caused an overlook of the tsunami threat. So what's behind this overlook? It's because the complexity of the earthquake rupture. We know that USGS reported 2 events. The first event is easily identifiable as there's no strong signal before it. But the second event is buried within the body waves and coda waves of the first event. Another thing that worth mention is that the South Sandwich subduction interface is not quite planar. It has a strong curvature as the incoming plate is retreating. And this challenges the conventional scheme to model and characterize the earthquakes. So here I listed some of those. Certainly we can have the location and magnitude sitting at this corner with very low adequacy of characterization of source complexity, but also quite unique. We have the focal mechanisms which in addition introduce the energy radiation pattern along different directions. Finally, we have a more sophisticated finite fault slip inversion, which discretizes the fault, usually the planar fault, into a series of usually hundreds to thousands of grids with different slip vectors. So these are good, but the problem is that none of those can handle these complex scenarios. The complex fault geometry, the complex rupture episodes, and the non-uniqueness of this most fancy slip inversion is huge. Think about it, 1,000 unknown parameters. So that's where we developed a multi-sub-event inversion scheme, try to tackle this problem and to fill the gap of the current earthquake modeling. So the idea is to characterize a complex earthquake into a series of different sub-events, each of those with distinct locations, timings, and focal mechanisms. So each of those can represent a slip header, a slip asperity, or a fault segments rupture. So this also provides an opportunity for us to lower the number of unknowns to slightly over 10 or several of tens, make it much easier to explore the parameter space. Sub-event idea is not the first being proposed by us. It actually been proposed by Kikuchi and Kanamori in the last end of the last century, where they developed method to iteratively deconvolve the contribution from each sub-event out of the seismograms. But the challenge is that the large sub-event can usually dominate the contributions because of the trade-offs. Think about a simple scenario when we are trying to separate the contribution of two Gaussian functions from a coherent signal. If we use the deconvolution to do that, we can easily put almost all of the contribution to the first signal, and then the second, the third is not going to get a lot of share. So only with an optimization-based approach can we adequately search for the source parameters of these different sub-Gaussians named sub-events. And we can see as the misfit goes lower and lower, the search becomes better and better, and the fitting is also more is also improved. So this is part of our development where we introduce a Bayesian Markov chain Monte Carlo optimization as an inversion driver. So this can explore the parameter space efficiently, and in addition, it provides us with uncertainty quantification, which is super important when we are thinking about earthquake source inversions. We also improve the efficiency of the algorithm by introducing a hybrid inversion in the forward loop to reduce the number of unknown parameters in the nonlinear inversion. Furthermore, we tried our best to include as many different seismic phases, including body to surface waves from the regional to teleseismic distances as we can, because this is very helpful if we think about the focal sphere. Different waves can sample the different region of the focal sphere and making the determination of the source parameters much better constrained. So with this development, we can now go back to look at the South Sandwich Island earthquake to see what happens. It seems that it does not consist one, not two, but 5 sub-events. The first event occurred at a magnitude 7.2 at a deeper depth. The second event occurred at similar location, not too far away, but transitioned to the shallower slab interface. The third event is a special one. It has a magnitude 8.16. It is an elongated rupture at a shallower portion near the trench for about 180 kilometers. And it has a slow rupture velocity of around 1 kilometer per second. It itself is strong enough to generate the global spread in tsunami. The fourth and fifth event is like anchors of where the rupture ends, and it shows the total rupture length of around 300 kilometers. So we see that the third sub-event is really special, not only because it's slow, but because it's large. And what I want to tell you in addition is that although it occupies over 70% of the seismic moment, it is really sneaky. It is silently hidden in the seismograms that we commonly analyze. The middle panel is a regular period seismogram at the global stations. The first row are the observations. We can see they are very well represented by the contributions from E1, E2, E4, and E5. And E3, it seems to be 0. Until we filter the data to over 300-second period, we can start to see the E3's contribution pop up. So this is really a important thing because the complexity in the rupture episode is really challenging our capability to unravel all of the rupture episodes and send timely and accurate tsunami alert. This time we are fortunate because the South Sandwich Island region is far away from the coastal communities, but we don't want this to happen again. So moving forward, we have attempted to make practical advancements in more quantitative tsunami prediction. This is an example of the 2024 Noto earthquake occurred last year. What we found is that it involved a delayed northeastward rupture episode, which substantially changed its tsunami pattern within the Japan Sea. You can see that the tsunami pattern is quite complicated. And with our sub-event model based tsunami prediction, we are able to reach a more accurate prediction of the tsunami arrival times, the amplitudes, and the waveforms received by the tide gauges. We can see that compared with the USGS finite fault slick model, our model is much better. So it really paved the way for the practical application of the new advancements in technology to the real-world hazard mitigations, and that's the direction where we are working together with the USGS. So go back to some science. Once we see the complexity, we need to quantify it. And where are the most complex rupture occur? Usually it's in the continental crust. And a representative example is the 2019 Ridgecrest earthquakes, where it's first magnitude 6.4 and then magnitude 7.1 34 hours later. They occurred in the East California shear zone, which is this dashed area. It's not the San Andreas fault, but it accommodates about 25% of relative plate motion between the Pacific plate and North American plate. After this event, we responded very rapidly, identified 100,000 of small events and relocated them, and found a stunning orthogonal interlock fault delineations indicated by this aftershock. See these force tails, see this a few of delineations cutting across a major fault trend from the northwest to the southeast. So then the question is, how are these faults ruptured? It's always challenging to evaluate whether a fault is ruptured or not during the cold seismic period or the aftershock stages. And to reach the fault mapping resolution when we are analyzing the seismogram and the cold seismic data, we need new advancements to overcome some limitations. From the data perspective, seismic data is really good at providing good temporal resolution, but the spatial resolution is really bottlenecked by the sparse station distributions. For the modeling, the sub-event provides good insights, but their implications need to be further quantified. And from structure perspective, our commonly used 1D Earth structure is not very adequate in this case because there is a channel-like basin very close to the fault zone. So that's where we made advancements. For the data perspective, we combined the seismic with the geodetic, including the INSAR and GPS, to provide a good spatial resolution as well. From the model perspective, we developed a sub-event guided multi-fault streak inversion framework that we can, based upon each sub-event's timing and location and focal mechanism, to build the fault geometry and test the resolution to the data set. And eventually, we incorporated a 3D velocity model at Southern California, the SCAC CBM, to calculate the Green's functions. So with this advancement, we are really to be able to differentiate the tiny details hidden in the data. For the magnitude 6.4 foreshock, we found that with one single fault plan, we cannot really fit the initial wiggles of the seismic and geodetic data. Only with the two faults, at least, or one trending towards the northwest direction, we can fit the data very well. For the magnitude 7.1, we found that the rupture initially are bilateral, but then unilaterally propagate towards the southeast direction. And when we are trying to evaluate the fault geometries, we encountered a problem. We are first trying to follow the surface rupture traces where there's a kink of the strike, but then we found that it cannot predict the regional strong motion and the teleseismic P waves. We can see that the fittings are really, really bad. But then we say, let's try to believe our sub-events. Think about the faulting geometry inferred from sub-event moment tensors. Then it's a through-going fault. And we can now better fit the strong motion and teleseismic data. But the insides start to show a lot of chunk of yellow. These are the line of sight misfits. So eventually only with a through-going fault, but with fault strength connecting the surface rupture and the deeper slip, can we best fit all of the data sets. So the implication here is that there are multiple surface fault strengths are coherently connected with the deep through-going fault, and the deep slip seems to be a driver of the shallower multi-fault, multi-strand ruptures. This is important because multi-fault rupture can really extend the rupture area and the final magnitude of an earthquake. And the Ridgecrest is potentially not the only place because it only represents a small portion of the Southern California and many other fault zones. We can somewhat identify where the fault is at the surface using the geologic record, but what about the structure at the deep? This is something we should rethink in the hazard assessments. So given these unknowns regarding what is inside the Earth, we should move forward to probe into the complex environment. And one of the most complex tectonic structure on Earth is the subduction slab. But here I want to focus on one specific type of event in the slabs called intermediate depth earthquake, which depths are around 70 to 300 kilometers. So this type of event is really strange. They should not occur because the temperature and pressure are so high to theoretically prohibit any brittle failure. But people have built up a really good theory about them. That is, the hydrated mineral at the outer rise region due to the faulting can carry the mineral water into the deeper depths, and then under the high pressure and temperature, it dehydrates, release the liquid water, build up the pool pressure, and allow the fault to slip. So the evidence is that there's usually a good coherency between the outer rise seismogenic zones depth range and also the thickness of the seismicity at the intermediate depth region. However, in the last year, there was a magnitude 7.4 earthquake occurred in the northern Chile intermediate depth zone with a normal faulting mechanism. And what is really intriguing is that the sequence of its main shock and aftershock seems to exceed the common seismogenic zone for the intermediate depth events indicated by these black dots. So what does it mean? Does it mean that this event has an out-of-bound rupture area being mobilized? We conducted the sub-event characterization of the earthquake. We found that it consists of 5 sub-events. The horizontal span of them are generally compact, rupturing towards the east for about 25 kilometers. But the vertical span, the depth range, are really large. The first and the last sub-event has a depth difference of over 50 kilometers, and it is spectacular considering it's within the subducting slab. It almost tears a majority part of the incoming oceanic lithosphere. And these depths are constrained quite tightly from both the teleseismic and regional strong motion data. These are only some representative data. And this steep faulting geometry get some support from the geodetic slip inversion as well. So to further quantify the down deep rupture extent, we take the advantage of the Doppler effect. Think about a car driving by us. The sound is first very sharp, and then when it drives away, the sound becomes lower. This is a Doppler effect, as the frequency really decides on the slip on the propagation vector of the car itself, plus the propagation of the sound. So in seismic wave, it's the same. As the station towards the rupture, we tend to receive shorter, narrower signal. On the opposite way and opposite direction, we receive the broader signals. And that's exactly what we see from the data. When we are looking at the downward P-wave source sine functions, they are really narrow. When we are looking at the upward source sine functions, they're really, really broad. So it's about 2 to 3 times of the difference. So we can collect these durations and then do a fit to understand the rupture length. Turns out that the rupture propagated down deep for 78 kilometers with a velocity of around 4 kilometers per second. It is really, really long. And it turns out to be really abnormal because when we are thinking about intraslab ruptures, it should be confined within the serpentinite dehydration zone if we believe they are caused by the mineral dehydration mechanism. But this one, when we are comparing it with a thermomechanical simulation using a realistic setting of the slab and including geometry and thermal parameter, it enucleated close to the coldest core of the slab, but quickly transcend the 650 isotherm, and then eventually reached a warm environment of around 1000 Celsius degrees. So this is quite abnormal because the other large intermediate depth earthquakes are usually prefer to stay within the comfort zone, right? They're all confined within the serpentinite dehydration area, and it's more intuitively observed from this base diagram. The x-axis is temperature, y-axis is the pressure, and for this TD earthquake, the initial rupture is within the mineral with quite sufficient water content. But the later stage, the second half of this rupture are all occurring in the dry zone. So the dehydration mechanism do not seem to be capable to support this part of the rupture. Then what do we need? We need a mechanism transition. The second half should have been transitioned to another mechanism, and the most likely candidate is the thermal shear instability, which we also call thermal runaway. The mechanism transition really allowed the earthquake rupture to go across this boundary and reach a larger rupture zone and larger final magnitude. And this is consistent with observation that the second episode of the rupture has a more complete stress drop, less aftershocks, and occupy almost 80% of the moment, because the thermal runaway mechanism is like heating based. When you already use the slip to heat the fault, it generates weakening, sometimes even melting at the fault tip. Then you allow the slip to have much larger extent to propagate to broader areas. So the insight here is that this dual mechanism transition really made earthquake larger. Now we have a series of things. We can observe the complexity, we can quantify them. We can also get an understanding of the environment. What should we do? We can try now to replicate the dynamics. And the example here is the 2023 Turkey magnitude 7.8 to 7.7 doublet. The Turkey earthquakes are not really much surprised because Turkey is a country with a long history of recording large earthquakes because of the existence of the two plate boundaries, the North Anatolian Fault and the East Anatolian Fault. So it's somewhat like we use two fingers to squeeze a ball. That's how Arabian plate is moving towards the Eurasia plate, and this squeeze made the smaller Anatolian block to move towards the west. It's like when the ball tries to slip out, the earthquake will occur at the boundary between the ball and our finger. So what is really surprising is that when we are looking at the intra-interferogram, we can see that these are the faults of the two earthquakes. They are very, very complex. They consist over 10 fault segments with very distinct fault geometries. And why? Because it's different from historical events. If we look at the historical events along the East Anatolian Fault, there are colored segments all around magnitude 7 and separated by kinks and stepovers. These are the geometric barriers. But this time, the magnitude 7.8 just brutally ruptured a series of segments so that the magnitude and length is much larger than expectation. The second magnitude 7.7 occurred on the very quiet Sugu Kadak fault, which has only had around a magnitude 6 event in the past several hundreds of years. So with the previous mentioned advancement in technology and modeling tools, and also combining the seismology and geodetic data, we are now able to unravel features from the data-driven models. We found that the first event initiated on subsidiary fault, but then it quickly propagated on the East Anatolian downfall, and it was able to overcome a series of geometric barriers. Here I use the slope signs to indicate them, and also surprisingly generated a delayed backward branching to activate almost half of the lung rupture. So this is unusual because the forward rupture tends to provide a stress shadow on the backward branch, and this is delayed. The delayed backward branching is quite well constrained by the data, where we can see that this 10-second delay model fit the strong motion pulses much better with a model without the delay. For the second magnitude 7.7, we found that the west part of the rupture has a super shear rupture speed. The super shear speed is like when an aircraft exceeds the sound wave speed, it generates Mach cones that can carry high amplitude of signals and carry it for long distances. So the super shear rupture can potentially cause a widespread damage, and this is something similar to what happened in the recent Myanmar earthquake. An earthquake occurred at Myanmar, caused a building collapse at Thailand, around 1,000 kilometers away from the source. So the data really requires the super shear rupture speed. Without the super shear, we cannot really predict the arrival time of the strong motion pulses. So given these observations, what we next need to do is to replicate them with the physics-based simulation. And the tool here we choose is the dynamic rupture modeling, where we solve for the spontaneous dynamic earthquake ruptures as the nonlinear interaction of the friction laws and also the wave propagations, the elastic wave equations. So what we need here is the fault geometry inferred from the observations such like the INSAR, GPS, and the strong motion data for the mesh generation. We also need the initial fault stress, as in this case we infer that from the long period, from the long time frame static sweep rate at the inferred from the geodetic data, and also the principal stress axis from the focal mechanisms. For the frictional properties, we choose to use something simple, although it's largely an inference. We choose the slip weakening as it's quite robust in the dynamic simulation. We eventually use the SISO solver, which is a high-order discontinuous scalicking method, and this provides us with a coherent rupture along the fault. So the simulation result from the dynamic models provide a very good replication of what we see from kinematic model. Here are the slip propagation or the rupture propagation on the faults. We can see how good the agreements are. So with these dynamic models, we can now see how the stress interact between different fault segments during the rupture. And we find that the magnitude 7.8 earthquake caused delayed backward branching because of the transient stressing and also the dynamic unclamping effect. The reason is that the forward rupture not only generates a stress shadow to reduce the shear stress at the backward branch, but also reduce the normal stress at the backward branch. And this is delayed effect. As the time goes, the backward fault is become loosened, and then the rupture can start to propagate. The second magnitude 7.7 super shear episode is from a heterogeneous pre-stress, which is a composite effect from the rotating regional stress orientation and also the rotating fault strike of the Sugu Kadak fault. And eventually, the first event seems to pose a positive stressing at the location of the second event. And among the two factors, the dynamic and static, the dynamic stress perturbation has a 1 order of magnitude higher than the static ones. So it could be potentially related to some transient effects, such like the fluid upwelling and the time-dependent erosion of the fault. That's how we can potentially explain the 9-hour delay between the two events. So I hope at this point I have convinced you that there are indeed a lot of complex scenarios, such like the multi-fault, multi-episode ruptures of the large event, and there could also be mechanism transitions, and they can really amplify the magnitude and the destructive potential of the earthquakes. With the investigation of their causes, including the fault geometry, the thermal and compositional environment, and the stress interactions, we can potentially better understand these factors and anticipate what future earthquakes behavior and impact will look like. So my talk is supposed to end here, but I also have several minutes to talk about some of my thoughts. One thought is that in the past several years, I have studied a series of large events with very different behavior of rupture complexity and processes. They span different tectonic environments, they show different appearance, also some ongoing work. If you are interested in the Myanmar earthquake, please feel free to reach me for discussion. But the idea is that, the question is that, how ubiquitous are these complexities? Are each of these events unique, somewhat unique in terms of the rupture, or are they actually hidden like mechanism that can somewhat control their commonality? So this requires a move towards the forward from the case study to systematic investigations. Most earthquake seismologists do case study because each earthquake represents a lot amount of work, certainly, and they are themselves good stories. But the thing is that if we want to better understand the earthquake physics and their controlling factors of the behaviors, we need to get a unified understanding from many different events, and also the statistical robustness is important as well. So here is an example that we have pushed the advancements of our inversion and modeling scheme to be able to apply for a series of large events. And our analysis have generated an unprecedented rupture catalog of all 40 magnitude larger than 7 deep events since 1990. And we are able to compare the rupture extent with the thermal condition and the compositional environment for all 7 subduction slabs hosting them. Eventually, we found that the dual mechanism transition seems to be more or less universal for these deep events. When they're small, they tend to be confined into the metastable olivine wedge, being pushed by the unstable mineral phase transition to occur. But when their rupture extend out of this region, they have to transition to a shear thermal instability mechanism, which can cause the complex fault geometry, increased stress drop, and the larger magnitude. We also attempted to analyze the complexities of a series of Chilean megathrust earthquakes. This is an interesting margin extending 2,000 kilometers from the north to the south. It seems that some of their source attributes are connected with the structural properties, such as their stress drop seems to drop from the north to the middle, then to the south. And this pattern is somewhat consistent with the average slab deep, and also the coupling properties along the subduction interface. So there could be a slab geometric control on the rupture behavior. Another issue is that their depth range of these ruptures seems to be consistent with the sedimentary thickness and some geologic processes related to the underplating and basal erosion. So it may indicate that the slab geologic process could set barriers for the down deep extent of these megathrust ruptures. These insights are helpful because if we make sure that these are true, if we do a physical replication of these things, we can potentially better understand these geologic controls and also structural controls, and then anticipate, to what extent the maximum magnitude are going to be at these regions. Another thought is about the scaling. So all the earthquakes I talked about are the generally magnitude 7+ events. They are huge. They cause a lot of impacts, but they are only a very small portion of the earthquake family. And this is a figure of the stress drop variability across the magnitudes from very small to very large. And we can see that not only there are variations over here, but there are also a lot of variation and potentially some trends at different stress drop measurements. Although there are large uncertainties of those, there are some good reason to believe that the smaller earthquakes can also be very complex. An example is one magnitude around 4 earthquake occurred in Oklahoma, where scientists have identified 4 sub-events during its rupture. So associating small and large ruptures is insightful to provide a pathway to connect the macroscopic to microscopic physical processes. One potential thing to do is to evaluate the source characteristics of the smaller events, such like we analyze the rupture directivities of small events during the Ridgecrest earthquake sequence, and identify different fault geometric properties, and they could be associated with the rupture physics, such as the stress drop and the maximum slip variations along the fault. Another is that this is some ongoing work I'm discussing with Charles. We are trying to collect the laboratory earthquake experiment data, and I'm trying to implement my expertise in the modeling and wavefield simulation to replicate what we see from that, and to determine the source characteristics and parameters. Some preliminary results seems that the simulation can somewhat explain the arrival time variations and some body wave features within the laboratory experiment data, which is good. So this is an opportunity to really bridge the empirical and theoretical understandings about earthquake source complexities. Please feel free to let me know if you have any additional thoughts. I'm always happy to discuss. Here I also want to acknowledge many of my advisors and collaborators from the Caltech Seismo Lab to the UC San Diego Scripps Institution of Oceanography, and then to here.